Hi everyone, my name is Jaya Barathi and I am from ECE department. Today I am going to discuss about the topic counters from the subject Digital Logic Design. For the counters, it is a sequential circuit. It is a sequential circuit. Circuit are of two types, combinational and sequential. Counters comes under sequential circuit. The definition of counter is it counts the number of clock pulses arriving at the input. Arriving at the input clock. Coming to the types of counters, there are of two types. First is synchronous. Next is asynchronous. The difference between synchronous and asynchronous will be at the arrival of clock pulse. Let's see in this detail. Coming to the synchronous, the clock will be same for all the flip-flops. Suppose I am taking A flip-flop and again I am taking B flip-flop. For synchronous, the clock will be given in common, will be representing CLK. Okay? For A and B flip-flop, we are giving the common clock pulse. Usually CLK is clock pulse. This is about synchronous counter. Coming to the asynchronous counter, again I am taking 2-bit, which means I require two flip-flops, A and B. The clock pulse is given to only first the flip-flop, that is CLK. You can write CP also. Okay. The outputs of flip-flop usually are Q and Q bar. Q and Q bar in A represents QA and QA complement. B flip-flop represent QB and QB complement. For A flip-flop, the only clock pulse is given. What about B means? QA will be acting as the clock, which means QA is the output of A flip-flop. This is about asynchronous counter. Coming to the modulus of a counter, we'll be representing with mod n. In case of mod n counters, the formula is 2 to the power of n greater than or equal to capital N, where small n represent number of flip-flops. Where capital N is the modulus of count. Let us take an example. Suppose if they asked about mod 9 counter and we have to calculate the small n, that is number of flip-flops, then if we substitute the formula, that is 2 to the power of n greater than or equal to capital N, always remember capital N is 9 here. 2 to the power of n greater than or equal to 9. Substitute the values n equal to 0, it will not satisfy. If we substitute n equal to 1, the condition is not yet satisfied. What if n equal to 4? 2 to the power of 4 greater than or equal to 9. 2 to the power of 4 is 16 greater than or equal to 9. What if n equal to 3? 2 to the power of 3 greater than or equal to 9. 8 is not greater than or equal to 9. So, the condition satisfied for n equal to 4. So, the number of flip-flops required will be 4. We will see a designing of mod 6 synchronous counter. using T flip-flop. For that, we'll be having few steps. The step 1 is find the type of flip-flop used. In this case, we can clearly see the type of flip-flop is T flip-flop. That completes step 1. Coming to the step 2, we need to find or calculate the number of flip-flops used. For that, in the question we can clearly see the mod 6. So 2 to the power of n greater than or equal to 6. Now if we substitute the value of small n, then 2 to the power of 2 is greater than or equal to 6, condition is not satisfied. Then we'll be going for 2 to the power of 3 greater than or equal to 6, condition is satisfied. So what about the small n value means? What about small n value means n equal to 3. In total, we required 3 flip-flops. Coming back to the next step, that is step 3, we need to write the excitation table of T flip-flop. For that, we need the present state and we also need the next state. Usually present state is denoted with Q of n. Next state is denoted with Q of n plus 1. The combinations of 2 bits is 0, 0, 0, 1, 1, 0, 1, 1. Next, coming to the excitation table of T flip-flop, that is 0, 1, 2, 3. The overall output is 0, 1, 1, 0. This is the third step A part. Coming to the third step B part, that is state diagram. In the state diagram, the small n value is 3, which means 2 to the power of 3 is 8 states will be there in total, starting from 0 to 7. But in the question clearly they gave about mod 6, which means you will start the state diagram from 0 and you will end at n minus 1. 0 to 6 minus 1 is 5. Coming to the state diagram, you will have the state diagram starting from 0, 0, 0 or simply 0. It will go to 1, it will go to 2, it will go to 3, it will go to 4, then it will come back to the state 5 and from 5 it will reach to 0. In this, though we are having 8 states, in the state diagram clearly we cannot see 6th and 7th states, or else 6th and 7th terms, that is 1, 1, 1, 7 combination is missing, and also 1, 0 and also 6, that is 1, 1, 0 is also missing. The next step is the state table. Coming to the state table, first we'll have QA, QB, QC. Next, QA plus, the next states is represented with plus symbol. Next, we are using T flip-flop, so that's why TA, TB, TC. Coming to the combinations of the present state, the state diagram, or else it is having total of 8 states, 0, 0, all the combinations starting from 0 to 7. Four is 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. Clearly from the state diagram, we are not having the 6th states and 7th states. So this entire row will be of don't cares. TA is also don't care, TB is also don't care, TC is also don't care. Don't care. Coming from the state diagram point of view, 0, 0, 0 is 0, 0, 1. From 0 it went to 1. From 1 it went to 0. From 1 it went to 2. From 2 it went to 3. From 3 it went to 4. From 4 it went to 5. From 5 it again went back to 0. For writing the TA, TB, TC, we need the excitation table of T flip-flop. Whenever we are having 0 and 0, from the excitation table, TA will be 0. Whenever we are having 0 and 0, from the excitation table, TA is 0. Whenever we are having 0 and 0, the excitation table clearly says 0. Whenever it is having 0 and 1, the combination is 1. Whenever it is having 1 and 1, the combination is 0. Whenever it is having 1 and 0, the combination is 1. Similarly, we have to write it for TB and TC also. For TB, you have to see QB and QB plus. What is the first combination means? It is 0 and 0, 0. 0 and 1, 1. Next is 1 and 1. Last combination it is 0. Next 1 and 0. Next is 1. Next is 0 and 0, 0. Next is 0 and 0, 0. For TC, we have to see the present state of QC and the next state, this is plus, next state of QC plus. The first combination is 0 and 1, that is 1. The next state is 1 and 0, 1. The next state is 0 and 1, 1. Next state is 1 and 0. For 1 and 0 also it is 1. Next 0 and 1, 1. 1 and 0, 1. This completes the table of the counter. Coming to the design part, we have to clearly write the minterms of TA and minterms of TB and also the don't cares. Minterms usually represented with summation M, don't cares usually represented with summation D. Coming back to TA, the minterm is present at 3 and 5. Minterm is at 3 and 5. Coming to the don't cares, it is 6 and 7. Coming to TB, the minterms is and the don't cares. Clearly the don't cares are at 6 and 7 combinations. Coming to TB, the minterms are at 1 and 3. Clearly for TC, we are having summation M. For TC, we got all ones and remainings are don't cares. The minterms are from 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. And coming to the don't cares, all are having don't cares at 7. Okay. For TA, TB, TC solving, we need 3 variable K-map. For 3 variable K-map. TC will be coming directly as 1. Why? Because we are having the minterms here and don't cares here. We have to solve using the 3 variable K-map and we'll be getting the equations for TA, TB, TC. Likewise, we can design. Thank you.